I want to review a little bit. So let me get into share screen, the usual routine here. Hopefully this will work quickly. Okay. Sometimes it takes its time. I don't know why. Sometimes it requires more than one try. Let me stop it and try. Okay, looks like that got it then. But let's see here. Let me lock this into place. All right, good. We got it. Yeah, so I just got a couple of minutes. Let me review where we were. We just got started on parity in the last lecture. Parity is another symmetry. The idea is this, is that the matrix I call P here, otherwise given a name, spatial inversion, has just got -1s down the diagonal. It just inverts all vectors through the origin. And if we throw it in with SO3, the proper rotations, and form all possible products that can be formed, we end up with the group O3, which is a set of proper plus improper rotations. Now, elements of SO3 were mapped into unitary operators, what we called U of R. We spent some effort doing that, and we called those, well, that was just the notation for it. We can put it in axis and angled form, but we did that only for proper rotations. What we're kind of looking for now is something similar, that P is going to be mapped into a unitary operator U of P, which we'll give a special name for. We'll call it pi and give it the word name of parity. And this is the operator on the Hilbert space of a quantum system that implements the action of spatial inversion at the level of the classical geometry. Now, the parity operator has to satisfy certain postulates, and we've listed them here, 1, 2, 3. One is that it should be unitary. This is the usual requirement on symmetry operators, that they be unitary in order to preserve probabilities. Second one is that pi squared should be the identity. That's because p squared is the identity, as you can see by looking at it. And the third one is that, excuse me, is that pi should commute with proper rotations, or rather the unitary operators that implement proper rotations, because that's what p does at the classical level. It commutes with all proper rotations R lying in SO3. And that's simply because P is a multiple of the identity. It commutes with all 3x3 matrices. In any case, this is a requirement that we impose on the parity operator in quantum mechanics. Now, if it commutes with all proper rotations U of R, it commutes in particular with infinitesimal rotations, and therefore it has to commute with the angular momentum of the system, whatever that is. So these are postulates that apply for any quantum system whatsoever. The actual parity operator that we get depends on the nature of the quantum system, but these are requirements that are necessary across the board. An important special case is that of a spinless particle moving in 3 dimensions. We'll start with that as the first case. So you have wave function psi of x, and we guess that in terms of the basis kets, that pi should map the position eigenket x into -x, which is similar to what we do with the rotation operators U of R mapped x into Rx. You know, just moving the position over to a new place. And I quickly indicated in last lecture how this definition, this guess for pi, actually satisfies all 3 of these postulates, and therefore is suitable as a definition of parity. And in fact, what this implies in wave function language is that the wave function psi of x is mapped into psi of -x. So I think that's straightforward. That's, of course, how you no doubt learn parity in your first course. So that's a real quick review of the last bit of last Thursday's lecture. So before going on, let me ask if there's any questions about that process of defining parity. All right, if there's no question, I'm going to go ahead and start to derive some of the properties of parity based on this definition. Let's take a look at what parity does to various operators. Like I'm particularly interested in position, momentum and angular momentum. Let's take position first. Let's take parity, pi dagger, and let's sandwich it around X and see what we get. I'm going to put a hat on the X to emphasize that that's an operator. Let's deal with momentum later on. So the way to evaluate this is, one way to evaluate this is just to work on wave functions. If I have a wave function, let me get the proper pin here because I want one that forces me to write big. Let's take a wave function psi of X. I'll do this in kind of a 1D notation, but it's easy to generalize to 3D. If we apply pi dagger first, let's do that. Well, pi dagger, to put it aside here, pi dagger is the same thing as pi inverse because pi is unitary, but it's also the same thing as pi because pi squared is equal to 1. So pi dagger, and pi inverse are all the same operator. So this just maps this psi into psi of minus X. If we now apply the operator X hat, that just means multiplication by X. So the wave function gets mapped into X times psi of minus X. And then if we apply pi again, that's the third factor here. That just takes X and replaces it by minus X. So it turns into minus psi of X, like so. And what you can see then is that the net effect of these three operators is to act on the wave function by minus X. So pi conjugated around the operator X gives us minus X with a hat on it to indicate an operator. In fact, let me get a clean sheet of paper here down below and summarize that in a three-dimensional notation. It would be pi times X vector, pi dagger is equal to minus X. Now, what about the momentum operator? Well, the momentum operator is minus IH bar ddx, like so, in the X representation. So if X goes to minus X, it's plausible that P should go to minus P. And you can analyze this in more detail if you want, but this gives rise to the rule that pi dagger sandwiched from momentum takes it into minus momentum. So these are two important conjugation relations that parity satisfies regarding the position and momentum of the particle. It basically inverts both of them. If I now take the cross product of both sides of this, what I get is that pi sandwiched around angular momentum, pi dagger, is equal to plus L. Let's just say the minus signs cancel and form the cross product of the right-hand side. And so what we've got now is a collection of three different vectors for a spinless particle moving in 3 dimensions and their conjugation properties under parity. We see that some of them come out with a minus sign and some come out with a plus sign. I'll come back to that later on, but these are some specific examples. All right, so that's the case of a particle that has only spatial degrees of freedom and no spin. Let's now move on to the case of a particle that has spin degrees of freedom, but no spatial. It's approximation, of course, but let's suppose we have that. So let's just take our ket space, our state space, to be the span of the basis kets, which is Sm like this, where m runs from minus S up to plus S for a particle of spin S. And let's ask what parity does to this. Oh, by the way, I forgot to mention something. I mentioned up above in terms of the general properties of parity that it has to commute with the angular momentum of the system. And in fact, that's what we find by cross product, doing the cross product of the X with P transformation laws. We find that L is mapped into itself. So L, of course, is the angular momentum for a spinless particle in 3D. And we see that it satisfies. I mean, if this didn't come out right, then there would be something wrong with the theory, but it came out with a plus sign here. So that's good. Now, when we turn to spin, then essentially the only property we know about pi is that it should invert. It should leave the spin alone because that's the generator of angular momentum on this system. This is a statement that parity has to commute with all proper rotations. Okay, and let's see what this implies for what parity does to these states here. The S here, of course, is the spin of the particle, which is a constant quantum number, and I can suppress that if I want to. So let's take a look at pi acting on a basis state m like this. If I apply S sub z to this, I can, since a pi commutes with spin, by the way, this is the same thing as saying that pi commutes with spin. Let me write it that way as well. Commutator pi with spin is equal to 0. So pi commutes with all three components of spin. So this is the same thing as pi times S sub z acting on m. But S sub z brings out the quantum number, so it becomes m times pi acting on m, like so. And if I put parentheses around the pi acting on m, what you see is that pi acting on m is an eigenstate of S sub z with eigenvalue m. Well, so is the state M itself, and in fact, it's a non-degenerate state. So this means that pi acting on M must be proportional to M itself. Let me write the proportionality factor as eta, like so. This eta, as far as we know at this point in the argument, could depend on M, so let me put a subscript on it, eta sub M. So we discovered that the pi must map the magnetic states into themselves with a factor eta M that we're allowing here. All right, now then, so that's progress. Now let's take a look at what happens when we apply a raising operator to pi acting on M, like so. Let's do that. We can do this in two stages. If I let pi act on M first, that brings out eta M, which is a C number. So this becomes eta M times S plus acting on M. And I'm going to write this as eta sub M times Q times M plus 1, where Q is this square root that comes out from doing the S plus. It's the square root of S minus M times S plus M plus 1, which I get tired of writing, so I'm just going to call it Q. In any case, this is what we get by doing this in this order. However, S plus and pi commute, so we can do it in the other order as well. And now the S plus, so this is pi then. Now the S plus acting on M brings out Q and gives us an M plus 1. Q is a C number, however, so pi shines through it, comes over, and pi acts on M plus 1 and brings out the factor eta M plus 1 times Q times M plus 1. That's what's left over. Now these two things then have to be equal. And you can see the M plus 1s are the same and the Qs are the same. What's different is the etas. And so what we conclude then is that the eta sub M plus 1 is equal to the eta sub M. And that means that by recursion, these etas are actually independent of M. And so we end up with the conclusion now that pi acting on M is just equal to eta times M with no dependence on M whatsoever. Well, if eta doesn't depend on M, then it's basically just a constant on the Hilbert space of the system here. In fact, it's a characteristic of the particle, not of the state. One thing about eta we know is because pi squared is equal to 1, it means that eta must be equal to plus or minus 1. So I can write it this way as plus or minus M. Pi acting on M is equal to plus or minus M. And so the conclusion of this at this stage then is that by using the postulates that the parity has to satisfy on a spin system, we find the parity operator is a constant on the Hilbert space of the spin system, and the constant is plus or minus 1. And the arguments we've given so far don't allow us to determine which of those two signs it is. So now the question is, are there any further logical or appeal to experimental data or anything that would allow us to determine what that sign actually is? And the answer is that as long as we stay in the non-relativistic theory, the answer is no. There is no way. There is no physical consequence to that phase plus or minus 1. And in fact, the custom is just to take it to be plus 1 for all massive particles, electron, proton, and so on. If you do that, then what you get is you get pi acting on M is just equal to M. And what we say then, if we make that choice, is we say that pi is a purely spatial operator and does nothing to the spin. That's the normal point of view in the non-relativistic theory. One reason I'm raising the non-relativistic theory is because in the relativistic theory, in relativistic interactions, it's possible to create and destroy massive particles. And if you do, then the number of particles can change. And it turns out that in reactions like that, where the numbers of particles change, it turns out that in order to account for conservation of parity, so the parity of the initial state is equal to that of the final state, it's necessary to assign a particle, a parity to a particle based on the kind of particle it is, something that's called an intrinsic parity. And that's this plus or minus 1, which is then assigned, as I say, on the basis of the nature of the particle. Now, the details of this process depend on whether the particle is a fermion or a boson. In the case of fermions, it turns out that the only significance of parity is to a particle-antiparticle pair, which always has negative, this is called intrinsic parity, by the way, of the particle. So a fermion-antifermion pair has a negative intrinsic parity. You can't say whether the fermion or the antifermion is positive and the other one's negative, but if you choose one to be positive, then the other one has to be negative. So typically one would take the electron to have positive parity and the positron to have negative, but that's a convention to a certain extent. In the case of bosons, the intrinsic parity of the particle is determined. For example, you find that the parity of the photon is negative, it's -1, as is the parity of the pi meson. So I'll say more about that later on, but that's the nature of intrinsic parity. Intrinsic parity really requires a relativistic theory to be very comprehensible. And the intrinsic parity, as I just mentioned, is not needed in the non-relativistic theory because the numbers of particles don't change in any interaction. So whatever intrinsic parity you assigned would be the same on both sides of the equation and wouldn't matter. So as long as we stay in the non-relativistic theory, we'll make this choice and we'll just say that the parity of all the particles we see is just equal to +1. The photon is a bit of an exception because photons have zero rest mass, and so they're freely created in even non-relativistic interactions. And we'll say more about photons a little bit down the line. But in any case, that's the story of intrinsic parity. All right, now, so that takes care then of the case of the parity of spin systems. What about if we have a combination of spatial and spin degrees of freedom? That is to say, suppose we have a particle with spin, what do we do? Well, the basis states in this case can be represented as a tensor product of x times m, which I can write for short as just xm taken together. And it's logical to define parity on these basis states, x comma m, like this, to be an action which converts x into -x and doesn't do anything to the m. This is just a combination of the two transformation laws that we worked out by tackling spatial and spin degrees of freedom separately. And if we do this, then the effect on a wave function, psi m of x, a multi-component spinor wave function for a particle with spin, is an under parity. This goes into psi sub m of -x. The spatial variable changes sign and the m index doesn't change. Again, simple statement, in the non-relativistic theory, parity is a purely spatial operator and does not affect the spin. When and if we get to relativistic quantum mechanics, we'll see that's no longer true. The parity operator actually does involve the spin. It's quite an interesting result. There's a more intimate connection between spatial and spin degrees of freedom in the relativistic theory, I think, which is a hint of something quite deep about the nature of spin. But we won't see that in the non-relativistic theory. All right, so that covers the case of the parity operator then on systems of with and without spin, at least single particle systems. All right, now, so a minute ago I explained the conjugation properties for parity under various operators, vector operators. X goes into -x. Momentum goes into minus momentum, and angular momentum goes into orbital angular momentum anyway, goes into plus itself. Actually, all forms of angular momentum do under parity. So what we see is that vector operators have different transformation laws under parity depending on the nature of the operator. Now, the fact that these are vector operators means they all transform the same under proper rotations. In fact, that was the definition of a vector operator. I'll remind you that it was U of r, the vector operator v, U of r dagger. You conjugate the vector operator, what you get is r inverse acting on the vector operator. That's the definition of a vector operator. And all three of these operators, position, momentum, and orbital angular momentum, all satisfy this. They're all vector operators in that respect. But that definition only involved proper rotations. When we come to improper rotations, we find that some vector operators have plus signs under conjugation, others have minus signs. The ones that have minus signs are called true vectors, whereas the ones that have plus signs are called pseudo vectors. And basically all the vectors that occur in physics can be classified as either true or pseudo vectors. For example, the electric field is a true vector and the magnetic field is a pseudo vector. As we work that out, the transformation properties of the electromagnetic field. So the introduction of parity introduces a finer classification system of operators than we had when we were considering only proper rotations. By the way, we can talk about scalars and pseudoscalars. If I have a scalar was originally defined as something that was invariant under proper rotations. So that's the formula there. But when we include parity, we can, let's call one K and one W like this, we can distinguish two different types. One is that's invariant under parity, and the other one that changes sign under parity. One that's invariant is called a true scalar, and if it changes sign, it's called a pseudo-scalar. Notice that the signs are opposite what we have for vectors. The true vector changes sign, the true scalar does not. But this is the terminology that's used. So a true scalar is invariant under parity. And what's an example of a true scalar? Well, there's actually a lot of them. I mean, for example, x dotted into x, which is equal to r squared, is an example here. X changes sign, but two copies of them don't. So r squared is a scalar. An example of a pseudo-scalar would be the position vector dotted into the spin, like this, or the momentum vector dotted into the spin, because position and momentum would change sign under parity, but spin would not. And so these are odd under parity. And these occur in parity violating effects. For example, the Hamiltonian that, for example, one can write down a Hamiltonian which applies at low energy to give you the effects of the weak interactions at low energy. And it does not conserve parity, and it contains the p dotted momentum dotted into the spin as operators that appear in it. All right, so that's the example of scalars and pseudo-scalars. Now, speaking about things that either are or are not invariant under parity, there's a question about the Hamiltonian. Whether Hamiltonian is invariant under parity depends on the Hamiltonian. But we made a big deal of the fact that Hamiltonians that are isolated from their environment are invariant under proper rotations because the energy cannot depend on the orientation. And so the question is, and what about these Hamiltonians? Let's just take, for example, Hamiltonians for isolated systems, for starters. We can talk about interactions later on. For Hamiltonians that are isolated, the question is, sure, they commute with proper rotations, but do they commute also with improper ones, in particular with parity? Well, let's look at some examples. If we took a central force Hamiltonian, p squared over 2m plus v of r, like this certainly commutes with parity because p squared is a dot product of p dotted into p. Each copy of that is odd under parity, but the dot product is even, so the kinetic energy is invariant. And likewise, the radius r is the square root of the position vector dotted into itself. So although x itself changes sign, the dot product does not. So the radius vector r is invariant under parity. So all central force Hamiltonians commute with parity. And that's an important fact. We can generalize this to Hamiltonians of multi-particle systems in which the potential of interaction depends only in the mutual distances between the particles. An important example of that is the electrostatic Hamiltonian for collections of charged particles. And that covers a large number of Hamiltonians that are used in all areas of atomic, molecular, optical, condensed matter physics. It's basically electrostatic approximation, basically the first approximation you make in describing the dynamics of matter. And that Hamiltonian definitely commutes with parity, as you can easily check. However, the electrostatic approximation is only an approximation to electromagnetic interactions. In addition to the electrostatics, there are, of course, phenomena of magnetic interactions, there's relativistic effects, there's retardation, there's all kinds of smaller corrections and so on. And so the question is, if we throw those in, does the Hamiltonian, again, for an isolated system, does it commute with parity? And the answer is yes, it does. If you're talking about electromagnetic interactions, it does, even with all those effects included. For example, one of the relativistic effects is the spin-orbit interaction, which we'll talk more about later in a lecture or two. And it's proportional to L dot S, the orbital times the spin angular momentum. But each of those L and S are even under parity, as I just explained, so the dot product is even also. And so a term containing that is invariant under parity. And you'll find the other fine structure relativistic corrections are also invariant under parity. What about magnetic effects? You'll find that those are invariant under parity as well. In fact, this is a magnetic effect. You'll find that magnetic effects are invariant under parity as well, as long as they're internally generated, that is to say, produce the currents that produce the magnetic fields are inside the system. And we're talking about isolated systems now, so there is no outside fields, okay? As long as that's the case, it's still true that the Hamiltonian will commute with parity, of which the spin-orbit term is an example, actually. What about if we go on to talk about emission and absorption of radiation, further interactions with the electromagnetic field? Well, when an atom emits a photon, in general, its parity changes. So, but that doesn't mean that parity is not conserved. The reason is that you need to take into account the parity of the electromagnetic field, and in particular, the parity of the photon itself. Turns out the photon has a negative intrinsic parity. And so in the simplest emission and absorption processes, which are those of electric dipole transitions, you will find that the state of the matter, the parity changes on the emission of a photon. And the reason is that negative parity is carried off by the photon. But overall, the combined parity of the matter plus the field system is conserved. And all of these are ways of, I can summarize all this by saying that in electromagnetic interactions, parity is conserved. The same is true for the strong interactions. This is something that was established originally experimentally. Large amount of effort went into this in the 1930s, 40s, and 50s, doing experiments on strongly interacting particles, hadrons. And in all cases, it was possible to show that parity is conserved. Now, however, those reactions are generally relativistic, and so the numbers of particles are changing. And so it's necessary to assign, as I mentioned earlier, intrinsic parities to the particles that play a role in those strong interactions. For example, you find the pi meson. The pi meson has 3 charge states. It's got a plus and minus charge state and a neutral state. Turns out all 3 of them have the same parity, which is negative, the negative parity. These are in some sense the carriers of the strong force field. At least that's one way of looking at them. And they have negative intrinsic parity, just like the photon does. But if you take that into account, you find that the strong interactions conserve parity as well. And so there was a period in history in which people believed that conservation of parity was a fundamental physical law, just like you have rotational invariance for isolated systems. Space is isotropic is what that means. However, that nice idea was destroyed in the mid-1950s when it was realized that the weak interactions violate parity. In fact, they do so in an almost maximal way. If you study the low energy weak interactions, you'll see this. This was first pointed out and quickly demonstrated experimentally in the case of beta decay. It was actually the cobalt-60 nucleus. Some experiments carried out on that almost immediately after the theory was produced showed that indeed parity is violated in those beta decays. So in the weak interactions, parity is not conserved. Now the weak interactions, as the name suggests, are weak. At ordinary, that is to say, low non-relativistic energies, the type you'll run into in most condensed matter physics, the weak interactions are so small that they're, in almost all practical circumstances, are utterly negligible. And in fact, if you wanted to detect them, which people have done, it is extremely difficult to do so because the effects are so tiny. So for most practical circumstances at low energies, one can ignore the weak interactions and say that all Hamiltonians that you're going to encounter for isolated systems conserve parity to an extremely high degree of accuracy. Now, as the energy increases, however, the relative strength of parity increases. And at the energies of accelerators, it becomes significantly larger than it is at low energies, laboratory energies, tabletop laboratory energies. It's still quite small compared to the electromagnetic and strong interactions, but it's bigger than it was. If you keep extrapolating to higher and higher energies, much higher than are available in accelerators, you come to a prediction that at a certain energy, there's a unification energy, that all 3 forces, the strong, electromagnetic, and the weak, will all have the same strength. This has never been confirmed experimentally, but it's a current theoretical idea that there'll be a unification of these various forces at a high enough energy. In any case, that's roughly the story of parity and parity violation and its dependence on energies. All right. Now then, So Hamiltonians for isolated systems at low energies conserve parity to an extremely high degree of accuracy. That's part of the summary of what I'm saying, what I've been saying.
Do they predict that the unified interaction would preserve parity or violate parity?
No, it violates parity all the way out.
Okay.
Now, it's part of the standard model. Now, but if you want a deeper understanding of that, you better talk to a particle theorist and not me. Now, on the other hand, this does not mean that all Hamiltonians commute with parity, even at low energies. If you want something that breaks parity, it's easy to do it. You just introduce an external field. For example, an external electric field, gives rise to, if it's constant field E naught like this, there's a potential phi whose minus gradient is equal to E naught like this. And then the phi then is equal to minus the position vector x dotted into E naught. And then the charge in the electron, which is minus E times phi, you get a potential V, which is equal to charge E times x dotted into E naught. So this, for example, is the perturbing Hamiltonian Zeeman effect, or any effect where there's an electron in an external electric field. You can see that under parity, what happens is x goes into minus x, but E0, which is the background field, is just a vector of C numbers. So they commute with everything, including parity, so they don't change. So this whole V then goes into minus V under parity and gives you potentially a very strong parity violating effect. We'll see that this means that parity plays an important role in the Stark effect, which we'll talk about in a subsequent lecture. All right, so it's easy to break parity by introducing an external field.
If you were to consider the particles that are producing the external field instead of just having it be like disembodied, would that preserve parity globally?
Yes, it would. If you made the system large enough to include the particles producing the external field, then now you have an isolated system. And now you see parity is conserved again to this extremely high accuracy. What this would amount to is that E0 would now become an operator because it would depend on the other particles. And then when you applied parity to that also, it would change sign as well. It would become a vector operator.
Cool, thanks.
All right, good. Now, let's take a look at some implications for parity and energy eigenstates. This is an extension of what we did earlier with energy eigenstates and invariance under proper rotations. Let me begin by reminding you some of the logic that was applied there. If we have a Hamiltonian which commutes with proper rotations, and it commutes, of course, with the all three components of angular momentum, and so hj squared and jz are commuting operators. And I explained the linear algebra logic that we use in setting up simultaneous eigenstates. We call the quantum numbers of the last two operators j and m, and we look at what we call the stretched eigenspace. Let me call it S of jj, which is the eigenspace of the last two operators j squared and jz, in which m takes on its maximum value. Now then, we said that since h commutes with these operators, we can diagonalize h on the space sjj. And for the sake of argument, let's suppose we have, let's say it's a bound, as to say, normalizable bound energy eigenstate psi, such that h psi is equal to E psi of the Hamiltonian on that space. Certainly the Hamiltonian can be restricted to the space and you can diagonalize it. Whether it has bound states or not depends on the Hamiltonian. Let's suppose it does have at least one. We'll call it psi. This is also an eigenstate of j squared with eigenvalue jj plus 1. And it's also an eigenstate of jz of eigenvalue j because we're in the stretched space. Now, as I explained in earlier lectures, by applying j minus lowering operators, what we generated is a collection of two j plus 1 states, which all have the same energy. And this leads to the theorem that the energy eigenspaces, the bound state energy eigenspaces of isolated Hamiltonians consist of one or more irreducible subspaces under rotations, that's to say with definite j values, which are of dimensionality 2m plus 1. And that means that, 2j plus 1. And that means the Hamiltonian is degenerate, has the same value in each of these subspaces. And there may be more than one with the same energy, in which case you've got multiplicity of that. Something I also explained is that having more than one eigenspace of the same energy like this is unusual. It's not generic. It requires, if it's going to happen in some systematic way, it requires some some systematic symmetry that goes beyond rotational invariance, and that doesn't normally happen. It's unusual in physical systems. And so there's an addendum to this theorem which says that in most normal physical situations, the bound state energy eigenspaces of real Hamiltonians consists of precisely one irreducible subspace under rotations characterized by a J value, which is therefore two J plus one fold degenerate levels of the Hamiltonian. And that's how it is. I illustrated this in the case of the iron 57 nucleus, which has these three states with J values 1/2, 3/2, and 5/2. These are the first three excited states of the iron 57 nucleus, and here's the J value. So the degeneracies are 2, 4, and 6, like that. Now, let's see what happens when we throw parity into the mix. Parity commutes with J. That's one of the properties of parity. So parity can be restricted to that stretched eigenspace just as well. And if we assume, ignoring the weak interactions, which is a very good approximation, that pi commutes with the Hamiltonian as well, then it means that pi and h can be simultaneously diagonalized on this space. Or to put it another way, if there's a non-degenerate eigenvector of the Hamiltonian on this stretched space, then this must automatically be an eigenvector also of parity. This goes back to this theorem, which I think the number is 1.5 from the early lecture, which I've mentioned at least once or twice already this semester. The theorem is this, is that if you have two observables that commute with one another and you have a non-degenerate eigenstate of one of them, then it's automatically an eigenstate of the other one. Easy theorem to prove and gets used over and over again. So here on the space SJJ, if psi is a non-degenerate eigenstate of H on that space, since pi commutes with parity, since pi commutes with H, it's automatically an eigenstate of parity. Now that in turn means when you apply lowering operators, since pi commutes with parity, since pi commutes with J, it commutes with the lowering operators. It means that all these two J plus one states that are generated by applying lowering operators are also eigenstates of parity with the same parity. And so therefore the parity is a property not of the vectors, but rather the entire multiplet. And so these multiplets have not only a J value, they also have a parity value, which for example, in the case of that iron 57 nucleus, all three of them happen to be negative. They're all negative parity. But this is why if you look up tables of nuclear energy levels or even atomic energy levels, you'll find that it gives not only the angular momentum value, but it also gives the parity. It's because of this property. By the way, the fact that these two states, the 3/2 to the 1/2 transition, that was the photon, the 14 kilo electron volt photon, which is important in the Mossbauer effect. The fact that the parity is the same between these two states is an indication that this is a magnetic dipole transition. That's something we'll talk about next semester, but I'll just mention it now. That photon is a magnetic dipole photon. If it had been electric dipole, it would have changed the parity. Roughly speaking, the reason for that is because in electric dipole transition, the photon carries off negative parity because of its intrinsic parity of the photon. In a magnetic dipole transition, there's also like an L equals 1 orbital part, which carries another minus one parity. So the overall parity of the atomic system does not change under magnetic dipole transitions. Again, we'll say more about that later in the course. But without knowing anything about the nuclear Hamiltonian, you see, we can make statements like this. The Hamiltonian governing the behavior of those 57 nuclei. All right, so those are some facts about parity and energy eigenstates. Let me say something about parity and selection rules. Case of selection rules we considered earlier involved the dipole transition in a single electron atom, and we had a matrix element governing that had two single electron central field orbit wave functions, energy eigenfunctions, NLM and NLM primed, sandwiched around the position operator. And I mentioned that this operator, or rather this matrix element, governs the rate of the transition. We examined this matrix element using the Wigner-Eckhart theorem, and we found two selection rules, one in magnetic quantum number, that M must be equal to M prime plus Q, and also one on the L quantum numbers, that L must belong to the set L prime minus 1, L prime, and L prime plus 1. And sometimes I like to sometimes I like to summarize that by saying that delta L must be equal either to 0 or plus or minus 1, meaning this, giving the same content. Now, however, this is what comes from looking at proper rotations, which is what the Wigner-Eckhart theorem captures. What about improper rotations? When we consider, in particular, parity, when we consider parity, we get a further selection rule. And it works like this. Pi x pi is, of course, minus x. Here, let's do it right. Pi x vector pi dagger is negative pi, negative x, because x is odd under parity. Let's sandwich that between our states NLM and NLM with primes on the right-hand side. This is therefore equal to minus that same matrix element now without the pi's in there. This is the negative of the matrix element we're interested in. On the other hand, if we let the pi act to the left over here and pi act under the right over there, these NLM states are central force eigenstates. And they give us actually a nice example of multiplets, which are a single irreducible representation under rotations, all of which have the same parity. It's an example of this J pi characterization of these multiplets that applied in the iron 57 nucleus. These are central force eigenstates, and they have a definite parity. What is the parity? So to answer that question, we need to go back to the wave function. The wave function is RNL of R times a YLM of theta and phi. And if we apply parity to this, it doesn't do anything to the radial wave function because it doesn't do anything to the radius. The radius is invariant under parity. On the other hand, in our discussions of YLMs, which is now several lectures ago, I explained that has a parity of -1 to the L times the same wave function. Let me write this in Ket language. Is that pi acting on NLM is equal to -1 to the L times NLM. And notice in particular, the parity is independent of the magnetic quantum number. That's because it commutes with the lowering operators. So it only, in fact, it only depends on the L quantum number, and it's -1 to the L. So to go back to our matrix element, this left-hand side, if I let pi act to the left and on the right, I bring out a phase factor of -1 to the L plus L prime times the matrix element NLM, X in the middle, and then NLM with primes on the right. So these two things then can only be equal to one another, or let's put it this way, this whole thing is equal to 0 unless -1 to the L plus L prime is equal to -1. And let me clear some space here, because that condition is equivalent to saying unless delta L is equal to an odd number. So, oops, it's off the page. So by consideration of parity, we find that this matrix element vanishes unless delta L is odd. And that means that delta L equals 0 value, which is allowed by the Wigner-Eckhart theorem, has to be excluded on the basis of parity. And the total set of selection rules for this matrix element then are the magnetic selection rules, and then delta L equals plus or minus 1. All right, so this is the main role of parity and selection rules. This particular selection rule that delta L is odd is which turns into plus and minus 1 for electric dipole transitions. This is called Laporte's rule. And it is, I don't know who Laporte was, but I think he was an experimentalist who observed a rule by looking at the actual spectra. The rule was explained theoretically by Wigner, who understood that it was due to parity. And later in his life, Wigner said that was, of all of his scientific accomplishments, that was one he was most proud of. This is something that most people looking at Wigner's career wouldn't say, because he did some amazing things in other areas, and this is actually rather simple, but he took great pride in it. All right, so that's the role of parity and selection rules. Now, that's all I want to say about parity for now, unless there's any questions. Parity is one of the important symmetries. You can see we're marching through symmetries here. We deal with proper rotations and we've just now taken care of parity. Parity is actually a good deal simpler than proper rotations.
Going back to the, sorry,
Yeah, go ahead.
going back to the pseudo vectors and pseudo scalars, are there also pseudo tensors?
Yes, yes, you can have those as well.
Would those equal negative or positive? Because it's different for the scalar vector.
I think the sign would alternate with each order of each rank of the tensor. I think that would be the convention that one would normally use.
Okay, that makes sense.
Yeah, it makes sense, I think. This classification becomes particularly important in relativistic theories, but that's not to say it's not important. These classifications are quite important in understanding symmetries and invariants of all kinds of systems. All right. If there's no further questions about parity, then I'm going to move on to the next symmetry, which is time reversal. Proper rotations, parity, and time reversal are all actual examples of Lorentz transformations. If you include the boost, then you've actually got all of the Lorentz transformations. And what I'm doing here in a piecemeal way is picking off various components of the symmetries that are actually subsets of the Lorentz transformations. The ultimate way to, or the most fundamental way of dealing with these symmetries altogether is to consider the Lorentz group and the Lorentz invariants of theories. But of course, this requires a relativistic theory. So what I'm doing is somewhat ad hoc in that respect, but it's suitable for a non-relativistic approach, which is what we're taking for now. So let's turn our attention to time reversal. First, let me give you just the idea of time reversal in classical mechanics. If we take some motion like a diver diving off a diving board or planets moving around the solar system, and you imagine taking a movie of it, the motion presumably satisfies the laws of motion, Newton's laws, F equals ma, and so on for whatever forces are involved in the system, because we believe that Newton's laws are right. So we have a certain motion that we can take a movie of. Now let's run the movie backwards and play it backwards, and let's ask whether the motion that we observe in the movie is also physically a solution of Newton's laws. In other words, is it physically allowed? And the answer to that question depends on the nature of the forces, as you might expect. So to take a specific example, let's talk about, let's say, a charged particle moving in an electrostatic field. In that case, the equations of motion would be the mass times the acceleration, md squared dt squared of x. I'll do it in 3D, x of t is equal to the charge q times the electric field x of t, like this, electric field, okay? Now, the motion produced by the movie, let me call it the time reverse motion, xr of t. The way we run the movie backwards, this just gives, this is the same thing as x of minus t. That just defines xr of t. Now the question is xr of t a solution of Newton's laws of F equals ma, assuming that x of t is the solution? And the answer is yes, because if I differentiate xr of t twice, there's two sign changes because there's a second derivative of x of minus t. So the left-hand side is restored to a plus sign, and the right-hand side is a plus sign also, because there's a plus sign in this equation. And so the result is that xr of t is a solution of Newton's laws if x of t is a solution, if we define xr in this manner, the time reverse solution. So that works for charged particles moving in electrostatic fields. What about magnetic fields? If we put magnetic fields, then the force is equal to not QE, but rather it's Q over C times the velocity dx dt crossed into the magnetic field B of x of t. And in this case, it's easy to see that the motion is not time reversal invariant because the left-hand side does not suffer a change of sign because two sign changes cancel in the second derivative. But on the right-hand side, taking the derivative of xr gives us a minus sign. And so the sign of the right-hand side changes because you have a velocity in there and first power of the velocity appearing. On the other hand, you might notice, so in other words, if you take a movie of a motion of a charged particle in a magnetic field and you run it backwards, you don't get the motion of a charged particle in that same magnetic field. Actually, what you get is a motion of a charged particle in the inverted magnetic field. you can see if you change the sign of B as well as of the velocity, then time reversal invariance is restored. So this is an interesting fact that there's a different system for which the time reverse motion is a solution, not the original one, but a different one. In this case, reversing the magnetic field. All right, so that's a little bit about what happens in classical mechanics. What about in quantum mechanics? Let's take the Schrodinger equation. Again, let's take a charged particle in an electrostatic field for starters. So the Schrodinger equation is IH bar ddt of psi of x and t is equal to the usual Schrodinger equation minus h bar squared over 2m del squared psi. And then for the potential for an electrostatic field, we need to put q times the scalar potential phi of x. And then this multiplies psi of x and t over here, like so. Now, in the analogy of what we did in the classical problem, let's define psi r, the time reverse solution of x and t, to be equal to psi of x and minus t. Effectively, if you could take a movie of an evolution of a wave function, we just run that backwards. Now, the question is, is that assuming that psi of x and t is a solution, is psi r of x and t also a solution? And the answer is no, because the Schrodinger equation is only first order in time, not second order. So this ddt is going to give you a minus sign on taking the derivative of that with that minus t over there. And so the left-hand side will change sign and the right-hand side won't. So it doesn't work, even for a particle in an electrostatic field. Seems like that's different than classical mechanics. However, we can restore time reversal invariance to the quantum problem if instead of defining psi r this way, we introduce a complex conjugate. Because if we do, you need to complex conjugate the Schrodinger equation to convert psi into psi star, and that'll change the sign on I in the left-hand side, which will compensate the change in sign coming from t, and then overall the Schrodinger equation is restored to itself. So if we define the reverse motion this way, then it does work for motion in electrostatic fields. Let's write this in ket language by saying psi r of t as a time-dependent ket is given by not psi of minus t, that's the thing that didn't work. Not that doesn't work. But instead we need to introduce complex conjugation, which I'll denote by an operator I'll call theta here, capital theta. So in this context, capital theta is complex conjugation. And this is the operator that we call the time reversal operator. So the time reversal operator, if I can spell it right, the time reversal operator, it's not an operator that changes t into minus t. It doesn't do that. What it does is it changes wave functions into wave functions. In other words, theta is a mapping that takes the ket space into itself. And a vector in the ket space is mapped into another vector in the ket space. What this does is it so happens that it maps the ket vector of the time of the backwards motion at time minus t into the ket vector of the reverse motion at time plus t. That's how it works. Okay, now this is the time reversal operator, and our goal is to study it and to find out what it is for more general systems, general quantum systems, including spin and things of that sort. More or less what we did with Parity a minute ago, but now for time reversal. Before I do that, let me note some things. If I put in a t equals 0 in this equation up above here, then what this implies is that the initial conditions for the time reverse motion, here, let me write it somewhere else so I can write it bigger. The initial conditions for the time reverse motion psi r of 0 is equal to theta applied to the initial conditions for the unreversed motion. So theta maps the initial conditions of the original motion into the initial conditions of the time reverse motion. So if the time reverse motion is also a solution of the equations of motion, then one way to find it is just to reverse the initial conditions and then solve the Schrodinger equation for the time reverse initial conditions. If we apply that at the classical level, the initial conditions of the original motion p of 0, like this, x of 0 and p of 0, should be mapped under time reversal into the initial conditions of the time reverse motion. Well, that should be x of 0 and minus p of 0, because you need to change the velocity. For the charged particle motion electrostatic field, this is the mapping we need for initial conditions. So in comparison to the quantum problem, given that theta maps initial conditions of one into the other, what this suggests is that the time reversal operator ought to satisfy certain, need a new pad of paper here, certain conjugation relations, namely, this was a classical relation here. Let me draw a line, and so that down below it, I'll draw a quantum relation, so that we have the following properties: is that theta conjugating x, theta dagger, should take it into x, but theta conjugating momentum, theta dagger around momentum, should take it into minus p, because this is the
Excuse me,
analog.
I have a quick question.
Yes.
So I'm a little confused about why we're doing this. So in the classical case, it seemed like we came to the conclusion that time reversal isn't necessarily always true.
That's right.
And so how come when we made the same analog in the quantum case where we said, okay, well, let's let, psi go to psi of minus t, and it didn't work, why didn't we just conclude, oh, I guess it doesn't work in quantum mechanics, as opposed to like changing our convention to accommodate it?
Because we're interested in symmetries that the Schrodinger equation possesses, the quantum system possesses. And the naive transcription from classical to quantum mechanics gave us a classical symmetry that did not map into a quantum symmetry. Nevertheless, the Schrodinger equation does have a symmetry. But in order to achieve it, you've got to put in the complex conjugation. So this is obviously a version of a time reversal symmetry because it does what you want in reversing the time, mapping the backwards movie into an actual solution. That's the logic of it. We're interested in whatever symmetries the Schrodinger equation has, and this is the logical one to call time reversal with this complex conjugation. Quantum mechanics is more complicated than classical mechanics. I hope that explains it. I mean,
yeah, sure, thank you.
We're groping for definitions of these symmetry operators. That's exactly what we're doing here. We're guessing properties, and then we're going to work out what the operator actually is. All right, so in systems in which position and momentum operators are defined, we expect the quantum time reversal operator ought to satisfy these relations. Notice the contrast with parity. Parity inverted both x and p, whereas time reversal inverts only p but not x. It leaves the position alone. All right. Now there's an important conclusion from these conjugation requirements here. Oh, and by the way, before I go on, if I form the cross product of x with p, you can see that this tells us that time reversal should invert orbital angular momentum, like so. And whereas, remember, parity leaves orbital angular momentum alone. Given that it does it to orbital angular momentum, it's a good guess that it does it to all other types of angular momentum, such as spin. And so we'll postulate that as well. In fact, we'll assume that theta takes all angular momentum j into minus themselves. If this weren't the case, you'd get really an untenable and an ugly theory if you're trying to make some kinds of angular momentum transform one way and others transform another. Doesn't work very well. So in any case, these are reasonable postulates then that our time reversal operator should satisfy on any system. As far as L is concerned, it follows from these earlier ones involving x and p. All right. Now then, it turns out that an operator that satisfies these relations cannot be unitary. And that's the first thing we need to address. And you can see this by looking at the commutation relations of position and momentum. Let me write it out this way: is that xi pj minus pj xi is equal to ih bar delta ij, which is the position momentum commutation relations. Let me straighten this out here, make it look better. If I now take time reversal theta on one side, multiply that way, and theta dagger on the other side and multiply the other way, then on the left-hand side, the x's will go into themselves and the p will change signs. So what we get is minus xi pj plus pj xi. And on the right-hand side, what we get is theta and theta dagger sandwiched around ih bar delta ij. Now, ih bar delta ij is a C number. And so that commutes with ordinary operators. And if theta were a unitary operator, you could just remove it. You get theta theta dagger, which is 1. And the right-hand side then would become IH bar delta IJ. And so you'd find the right-hand side did not change sign, but the left-hand side does. And that's a contradiction, of course. So this can't work. And the way we resolve this apparent paradox is we say theta is not a linear operator, but it's rather an antilinear operator. Because if we do that, then the antilinear operator changes the sign of I. And when you pull the theta theta dagger through that C number, it changes into minus I, and therefore the contradiction is removed. This, by the way, was seen earlier when we talked about the wave function for a particle moving an electrostatic field. There, the theta operator was complex conjugation. Complex conjugation maps state vectors into state vectors, all right, but it's not a linear operator, it's an antilinear one. You could see it already in that simple example. But this shows that in general, theta must be antilinear. Now, so far in this course, we've only considered linear operators apart from very brief remarks that I made in my very first lecture. So the task before us right now is to put time reversal on hold and to make a digression into the properties of antilinear operators. And that's what I'd like to do now. The algebra of antilinear operators. The previous stuff is just the setup for time reversal. So let's let L be a linear operator and A be an antilinear operator, I think, just to distinguish between the two. Both of these are mappings of the state space into themselves. They take state vectors into state vectors. But they have different properties when acting on linear combinations of state vectors. So a linear operator acts on a linear combination C1 psi 1 plus C2 psi 2 and gives us C1 times L acting on psi 1 plus C2 times L acting on psi 2, the usual definition of a linear operator. That's what you mean by linear operator. Now, if A is antilinear, on the other hand, the A acting on the same thing gives us C1 complex conjugated times A acting on psi 1 plus C2 complex conjugated times A acting on psi 2. In other words, when an antilinear operator acts on a linear combination of vectors, the coefficients become complex conjugated. And this is a basic property of antilinear, the defining property of antilinear operators. This means that if a constant C is regarded as a multiplicative operator, which of course it is, then it does not commute with an antilinear operator, but rather goes over into C star. And let me box this and label this number 1, because this is the first of some rules by which antilinear operators differ from linear operators. I'm going to make some rules that'll help you to understand how to work with antilinear operators. This is the first one. The second rule comes from what happens when we allow antilinear operators to act on bras rather than on kets. Let me repeat some material from I think the very first lecture about this. Let's suppose we have the action of a linear operator on state psi. Let's say it's known. That's to say we know what the linear operator does to all state vectors. Let's suppose that's known. And what we'd like to do is to define the action of that corresponding operator on a bra like this. We want to define this. The definition that we used earlier was the following. The logic, we'll go through the logic again too. The logic is this, is that L by definition maps kets into kets. We want to enlarge the definition so that it's meaningful when it acts on bras. If psi is a bra, we write the action of L on psi by putting L to the right. That's just the convention for how we write that. When L acts on a bra psi, whatever the answer is, it's going to be another bra. That's how it works. Now, a bra, I'll remind you, can be regarded as a map that takes kets into complex numbers. In fact, it's a linear map. That's one way of defining a bra. So psi with L like this is a bra, therefore it acts on kets. I can allow it to do that, and when we do it, we get a complex number. And if I say what that complex number is for all psi and phi, I've actually defined the bra psi L like this. Well, the logical definition for this is to take the complex number to be psi, L acting on phi, like so. In other words, instead of letting L act to the left on psi, we let it act to the right on phi, and we call that the answer. Well, if we do this, and this is what we do, then the net effect of this is that it doesn't matter in what we call a scalar product, whether Lx to the left or to the right. And so we normally just drop the parentheses and we write it like this. And that's the logic of this. You can now think of L acting either way. It won't matter because the answers are the same. Okay, that's what we did with linear operators. Let's try the same thing with an antilinear operator. Let's say A is an antilinear operator and A acting on psi is known. What we want to define is psi bra with A acting on it. Let's try the same trick. Psi bra A acting on it is supposed to be a bra. So we'll let it act on an arbitrary ket, and the answer then has to be a complex number. Let's do the same thing before. Let's just guess that this is psi with A acting on phi. Exactly the same thing as before. The question is, does that work? Well, it does definitely assign a complex number to the value of psi A acting on phi. Psi A is supposed to be a bra. The problem is that bras are not just kets, maps of kets into complex numbers, but they're supposed to be linear maps of kets into complex numbers. And this, unfortunately, is an antilinear map. Because if I replace phi by a linear combination of vectors, then A acting on it complex conjugates the coefficients. And so the result is that this is an antilinear function of phi. We can fix that, however, by complex conjugating the right-hand side. Let me do that by putting brackets around it and star the whole thing. If we do that, then the right-hand side is now still a complex number, but it's now a linear functional of phi rather, and therefore it does define a proper bra. So this works as a definition. In fact, we'll take this as our definition. Let me write it out in a slightly different form. I'll put psi A like this with parentheses, and then a phi like so. And this then is equal to psi, and then A acting on phi with parentheses like that, and then the square bracket and complex conjugate it. And let me box this and put this down as rule number 2. Which is the second rule by which antilinear operators differ from linear operators. Now, you may be dismayed at this point by thinking, oh, this is a horrible formula and hard to remember. And I agree with you, it is. It's hard to remember if you try to memorize all the brackets and parentheses. But if you put it into words, it's actually quite simple. The words to remember are this. In the case of a linear operator, it doesn't matter which direction the linear operator acts in a matrix element, whether to the right or to the left. And so we don't usually put in parentheses. We just leave them out and write the matrix element. In the case of an antilinear operator, it does matter which direction it operates. And therefore, we need parentheses. Here, for example, indicate that the A acts to the left, and here that it acts to the right. That's what these parentheses do. So the parentheses are necessary. Moreover, if we change the direction in which the operator acts, like to saying, oh, I don't want it to act this way, I want it to act the other way, we can do that, but we need to complex conjugate the answer. And that's just what this formula says. If I reverse the direction which A acts, I need to complex conjugate the result. So if you remember that word, that rule in words, you've got this formula down without having to remember all the complications of it. So that's rule number 2. We move on to rule number 3. This has to do with the definition of the Hermitian conjugate. If I have a linear operator psi, which again we say is known, we wanted to define what we call the Hermitian conjugate operator, L dagger. This is another linear operator, is equals question mark. We want to define this. How did we define it? Well, if you look back, the way we defined it was we said L dagger acting on ket psi is given by bra psi with L acting on it from the right, the whole thing daggered. In other words, in words, to compute the L dagger acting on psi, what we do is we first use the metric to convert psi into a bra. Then we let L act on the bra from the right, which we know how to do because I just explained that. And then we dagger that result, which converts it back into a ket, and that's the value of L dagger psi. Now, L dagger is a linear operator. The process of converting psi into a bra is antilinear. But when we do the dagger, it's a second antilinear operation. So overall, the right-hand side is a linear function of psi, and that means that L dagger is a linear operator. Now, will this work for, oh, and let me show one more thing too. Let's give this a name. Let's call this alpha is equal to that. This means that alpha as a bra is equal to the dagger of that, which is equal to psi L, like so. So then if I have a scalar product phi with alpha, then this is equal to phi L dagger psi, like so, just doing it up here, multiplying by bra phi. But this is also the same thing as alpha scalar product with phi complex conjugated, which is therefore equal to alpha, which is therefore equal to, using this, it's psi L phi complex conjugated. In comparing these two things, you see an example of the rule, the general rule in the Dirac formalism, that if you have an object and you want to take its Hermitian conjugate, you just read it backwards and you Hermitian conjugate all the various factors. So psi goes, ket psi goes into bra psi, L dagger goes into L, and bra phi goes into ket phi. But we star the whole thing because Hermitian conjugation of a complex number is the same thing as complex conjugation. All right, so that's the rule I'm sure you're familiar with. Let's try this now for antilinear operators and see what happens. Let's suppose that A acting on psi is known. And we want to say, what is A dagger on psi? What's the meaning of this? Equal to question mark. Well, let's try the same trick. Let's say that this is equal to psi A, like so. We know what A does to bras. We just worked that out. So this is well defined. Allow me to do something similar to what I did before. Let me just call this a ket vector alpha, like so. Oh, excuse me, I didn't say that right. This should have been daggered. So this is just copying what we did for linear operators. So A dagger acting on psi is defined this way. It's the same story. We take psi, we by the metric convert it to a bra. We let A act on the bra, and then we dagger that to get back to a ket again. And by the way, this makes this into A dagger into an antilinear operator, since A itself was. There's three antilinear operations over here. One converting ket psi to bra psi, a second one by multiplying by A, which is antilinear, and a third one by daggering again. So A dagger is antilinear if A is antilinear. All right, now then let's do what we did before. Let's form the scalar product phi with alpha for some state phi. This then is phi scalar product with A dagger psi, and I put parentheses. I have to put parentheses. Let me write it better so you can see it better. It's phi scalar product with A dagger psi, and I put parentheses around that because this A dagger is acting to the right. All right. Now, on the other hand, that's the same thing as alpha phi scalar complex conjugate. And alpha, if this is alpha ket, then alpha bra is just equal to psi A, like so, converting this around, daggering this, you see. So this becomes psi A, and I put parentheses there because this A acts to the left now, you see, multiplying onto phi. And I have to complex conjugate because that's the same as a star there. So to put this all together then, let me write it this way, let me combine these things into a single equation, is that phi A dagger psi, with the A dagger x to the right, is equal to psi A, where the A acts to the left, scalar product with phi. This whole thing was complex conjugated. Let me box that because that's rule number 3. Now again, rule number 3 looks like a horrible formula to remember, but once again, it's easy to do it in words. So the words is this rule about Hermitian conjugating an object by just reading it backwards and Hermitian conjugating all the various factors. It also works for antilinear operators, exactly the same, but with one further issue, which is that there now are parentheses to indicate the direction in which antilinear operators operate. And so when you read things backwards, you need to read the parentheses backwards also. So here, for example, if I've got this thing on the left-hand side, which is a matrix element, and I want to form its Hermitian conjugate, which is the same as the complex conjugate, then what I do is I read it backwards. So on the right, I've got a right parentheses. So that start with the left parentheses. I've got ket psi over here, that turns into bra psi. I've got an A dagger, that turns into an A. I've got a left parentheses, that turns into a right parentheses. I've got a bra phi, it turns into a ket phi. And the star here is coming because by reading it backwards, I'm permission conjugating the whole thing. So if you follow that rule, you see this is really not, this is just a slight generalization of the rule you know already. That's the way to remember this one. All right, now then. Okay, so those are the three properties of antilinear operators that differ from linear operators.
So I have a question regarding this. You briefly mentioned that it's a matrix element. So that reminds me, like, if we want to write it as matrix element, if we want to write an antilinear operator as their matrix elements, then is it a convention to have the A acting on the right or to the left?
You've detected the flaw in my language. I shouldn't have called it a matrix element. I should have called it a scalar product, because that's what it is. It's a scalar product of phi with this vector in the parentheses there. To interpret it as a matrix element, you're quite right. You need to worry about which direction do you act in. So let's not get into that. You don't really, practically speaking, you don't need to. Let's just not call it a matrix. It's really a scalar product.
Okay.
Okay.
So does that mean that antilinear operators cannot be written as matrix elements, or is it true that?
Well, no, if you're willing
specify.
to agree which direction it acts, you could talk about a matrix that's associated with the operator. And if you had a basis, for example, but you'd have to decide which direction it's going to act, right or left. It wouldn't be the same.
Okay.
And I think it's actually in practice, it's not as convenient as what you do for linear operators.
And my other question was, like, are there like examples of antilinear operators that we would encounter?
Time reversal is the main one.
Okay.
Yep. Antilinear operators appear in, well, I could argue they're all connected to time reversal. Antilinear operators are actually important in representation theory. If you want to get into even the theory of SO3 and so on, they're actually quite important. All right. Now let's see. All right. So this was a digression into the mathematical properties of antilinear operators. So I hope that there doesn't sound too complicated and we can actually use them now. I'd now like to address the issue of not just antilinear operators, but anti-unitary operators. Unitary operators we usually invoke them for symmetry operations. We said symmetry operations had to be implemented by unitary operators because we wanted to preserve probabilities. It turns out antilinear operators also preserve probabilities. This is related to a famous theorem by Wigner, which I'll just mention briefly. Wigner showed that if you have a mapping of the state space onto itself that takes, let's say, state vector psi into prime versions of themselves, some map does this. And if you wish the scalar product of state vectors, the absolute value of the scalar products, to be mapped into themselves under this transformation, psi prime scalar product with phi prime, for all vectors psi and phi, then he proved that the operation must be either a linear unitary operation or else an antilinear unitary operation. It's a famous Wigner symmetry theorem. Now, Wigner only requires that the matrix elements be mapped into the absolute values of the matrix elements be preserved, not the matrix elements themselves. And the reason is that the probabilities, which are physically measurable, are the squares of those things, and so you can't tell the difference. So you want to limit it. Anyway, you need antilinear operators in general for symmetries. Now, in fact, all the symmetries that we encounter in quantum physics, certainly proper rotations and parity and translation operators that we've talked about already in this course, are all implemented by means of unitary operators. But time reversal is the oddball. It's the one that requires anti-unitary operators. In any case, now let me tell you what an anti-unitary operator is. So we'll say an operator A is anti-unitary if it has the following properties. The first one is that it is antilinear. And the second one is that it satisfies A times A dagger is equal to A dagger A is equal to the identity. By the way, it's kind of an obvious property of antilinear operators is that if you multiply two of them together, you get a linear operator. So A times A dagger or A dagger A are both linear operators, and they're if they're antilinear, the operator has to be equal to 1. It does not make sense to take an anti-unitary operator and set it equal to 1, because 1 is a linear operator, not antilinear. You can't equate an antilinear operator to a linear one. It makes no sense. All right, anyway, this is definition of antilinear. It's kind of obvious. Let me show you some properties of antilinear operators. In particular, I want to show you that they preserve probabilities in the sense of Wigner. So it works like this. If I can get a single page of paper torn off here. Let's suppose I take a ket psi and I act on it with an, let's let A be anti-unitary, because I want to explore the properties of anti-unitary operators. And let's let A act on psi. Let's call the new state psi prime. And let's do something with phi is equal to A phi prime. A phi is equal to phi prime like this. Now let's consider the scalar product psi prime with phi prime. The psi prime is a bra version of the equation I wrote up above. So this is the same thing as psi is a bra times A dagger. And I put parentheses around that because this A acted this way, you see. So this A dagger is acting that way. And then for the phi prime, this is A times phi. And I'll put parentheses around that to indicate that the A acts to the right. All right. So that's what this product is. Now I'd like to change the direction in which that A dagger acts to make it move in the other direction. So this then becomes psi on the left, A dagger A phi. And I'll put parentheses around that now to indicate that these are all acting to the right. But I have to complex conjugate the whole thing because I changed the direction in which A dagger acts. But A dagger A is equal to 1. So this is the same thing as psi scalar product with phi complex conjugated. And so to summarize it in a single line, I have psi prime scalar product with phi prime is equal to psi phi complex conjugated. So an anti-unitary operator does not map matrix elements, or excuse me, scalar products into themselves. It maps them into their complex conjugates. But the absolute values, or the squares, which are the measurable probabilities, are mapped into themselves, and that's what counts physically. All right, so antilinear operators for that reason are suitable for symmetry operations. Now, next I'd like to tell you about what I've called the LK decomposition of an antilinear operator, or an anti-unit, or an antilinear operator, not necessarily anti-unitary, but any antilinear operator decomposition. I'll tell you what I mean by this. So we've got some antilinear operator that might be complicated. What we do is we find an antilinear operator which is simple, and then what's left over, if I can factor out what's left over, must be a linear operator, and that's what the L is. So the idea is that the K takes care of the antilinearity of A, and the L takes care of everything else. It's convenient to do this factorization for antilinear operators that occur in practice, and I'll give you some examples, probably not tonight because there won't be time, but that's the idea. Let me explain this LK decomposition. The K operators that occur here are usually of a certain type. Let's say I have a complete set of commuting observables that I'll call Q. Q is really a list of observables, it could be, depending on the system, that commute with one another. And let's write the eigenstates of the Q is in this form. Let's call the quantum numbers n like this, so this is equal to n times n. And in itself is a series of quantum numbers for the different components of Q, and some of them could be continuous and some could be discrete. This is a highly abbreviated notation that I'm using here, like this. Now let me define an antilinear operator associated with this complete set of commuting observables and call it K sub Q. And it's defined in the following way. So KQ, the definition of KQ is the following. The first one is that KQ is antilinear. And the second part of it is that KQ, acting on the basis states n, just maps them into themselves, leaves them invariant. Now let's notice that if KQ were a linear operator, the second equation here would imply that KQ is the identity because it maps every basis state into itself and therefore any linear combination into itself. However, the identity operator is a linear operator and KQ is antilinear. So not only is KQ not equal to the identity, in fact, it wouldn't even make any sense if you wrote that equation down. It's a meaningless equation. So this defines KQ. Now this KQ defined in this manner, let me show you that its principal property, and then I'll because I'm running out of time, and I'll explain in more detail in the next lecture. If I apply KQ to an arbitrary state psi, and let's say I expand psi in the given basis to sum on in some coefficients n like this, then because KQ is antilinear, the coefficients get complex conjugated. But the KQ acting on n by property number 2 doesn't do anything. So the n's just repeat like this. So you can see that the effect of KQ is, well, so I'm here, what I'm using is I'm using psi as expanded in the basis as CNN like this. Remember, a wave function is nothing but the expansion coefficient of a state vector in some basis. So the CNs here are the wave function of psi in this Q representation. And you can see what KQ does is it maps psi into a new wave function in which into a new state, which has the complex conjugated wave function. So this KQ operator, in other words, is the complex conjugation operation in the given Q basis. That's why it's simple. It's simple in the basis Q anyway. Now, one further remark is that this KQ operator depends on the phase conventions for these basis vectors. So it actually is not just dependent on Q, the complete set, but also on the phase conventions for the basis states. But I'll use the notation KQ anyway for that. Anyway, this is the nature of the simple antilinear operator that's frequently used in these this LQ decompositions. And in next lecture, we'll give you an example of that. All right, I ran over time a little bit, I'm sorry. That is all for tonight, unless there's any lecture, any lectures, too many lectures, unless there's any questions. Any questions?
Hi, sorry, I just have a short clarification question on one of the homework problems. The homework problem asks us.
Sure.
It asks us something along the lines of, if one of the components of a vector operator vanishes, show that they all do. And I was wondering what's meant by that. What is meant by one component of the vector operator vanishes?
So operators are mappings of ket vectors into ket vectors. And the three components of a vector operator are operators. So if I say that one of the components vanishes, it means the operator is the zero operator. It maps all vectors into zero.
Okay, great. Thank you.
Okay. All right. Any other questions?
Yeah, I have a question. For the other symmetries, it seemed like they all had a symmetry group associated with them. Does
Yes.
the time reversal symmetry have a group, or can it not because it doesn't have?
No,
Yeah.
time reversal. I mean, if you look at it at the classical level, it's time reversal. It switches t to minus t. That's the symmetry of the Minkowski metric in Lorentzian spacetime. It's a space-time symmetry. So parity is another one, and ordinary rotations are, and then finally there are Lorentz transformations, those that form the complete Lorentz group symmetries.
Okay. So yeah, so you have to consider them all together.
Yeah, a unification of all these symmetries takes place in a relativistic theory. You'd learn this in courses like 232.
Yeah, there's so many dumb things.
Are there any other questions? All right. If there's
yeah, I have a question. Sorry.
yes.
So if there's an anti-unitary operator such that a dagger A is the identity, then then if we insert, let's say if there is some product of operators, or even let's say there's some psi and psi star bracket thing, and we insert the identity by saying we insert a dagger a, then it seems like if we write that as the identity, then that's a linear operator, so it doesn't matter if it acts to the right or the left.
That's right.
But if we write it as a dagger a, then it seems like it would matter if it's acting to the right or the
Well,
left.
you see, it's a product of two antilinear operators. So if you write it as a dagger a, what you mean is it's probably best to think of them as both acting to the right. The first, the a acts, and then the a dagger acts, you know, on a ket. Think of it that way.
Oh, so then is the difference going to be
That's what a
the same-
dagger a. That's what a dagger a means. I mean, if you think about if you think about these antilinear operators as mappings of the ket space onto themselves, then a dagger a is just the composition of the two maps. That's all it is, and you just write in that order. But that's a way of saying that they act to the right. Now, if you wanted them to act to the left, you could do that. You can go through the rules that I've just given, and you can see how it works.
Oh, okay. So then that means it's either both act to the right or both act to the left.
Yeah, if you wanted your a dagger a to act to the left, you could do it one step at a time. You could first do the first factor and then the second factor. You get two complex conjugations which you cancel out.
Right. Okay. Okay.
Okay. And that would make sense, because if it were, if it were anti-unitary, then you get one. Acting to the right and the left would be the same.
Right. Right. Okay.
Yeah. Okay.
Thank you.
Any other questions? It seems like a big investment to learn all this antilinear operator stuff just for the sake of time reversal. And it depends on how much you're interested in time reversal, but it turns out that it's more important than you'd think. It's actually plays I'd say it plays a major role in understanding the fundamentals of symmetries and certainly in molecular and condensed matter physics. Atomic molecular and condensed matter physics certainly does. Optical physics as well. Any other questions? All right, if not, I shall begin by stopping screen share. And then I'm going to stop the recording.